Once we have the notion of isometries, we cannot not talk about the group of isometries. So let's study groups of isometries of quadratic spaces. For a quadratic space V, we denote the group of isometries of V by OV. And as usual, we want to use the tools of linear algebra, so we want to think of this as a matrix group. How do we do that? Well, if the bilinear form of V has a gram matrix A in some basis, then we can give the following description of the isometries. So an isometry, first of all, has to be an invertible linear transformation. So if we have an isometry sigma, we can view it as a map in the general linear group, which must be invertible linear transformation. Now, to be an isometry, it must preserve the bilinear form. And so if we look at the matrix corresponding to this bilinear form, we have this identity. From this identity here, we see that the determinant of t squared, must be 1. So the determinant of every isometry in this group OV must be either 1 or minus 1. So we split this group into two parts. The isometries with determinant 1 form a group, which we call the rotation group and denote by O plus V. And the rest of the isometries, we call them O minus V. This, of course, is not a group. So now let's look at an example. Let's try to compute the isometry group of the hyperbolic plane. We claim that its plus and minus component consist of these matrices, and let's see why. Okay, so how would we figure out the isometry group of the hyperbolic plane? We want to look at some invariant. Now, an isometry must preserve isotropic vectors because it preserves the bilinear form. So if sigma is an isometry, then sigma and v1 is an isotropic vector, then sigma v1 is also a zero of the quadratic form, but the isometry has to be invertible, so sigma v1 can't be zero, so it must be isotropic also. Now, if the hyperbolic plane has this matrix in this basis, then this means that v1 is an isotropic vector and v2 is an isotropic vector, and these are all of the isotropic vectors. Because for any vector in the hyperbolic plane, we can write it as a linear combination of v1 and v2. And when we compute this out, then this norm is just going to be, quote-unquote norm, is going to be 2 alpha beta. So this is 0 if and only if one of these is 0. So that is if and only if this vector lie in the span of either v1 or v2. Thus, these are all of the isotropic vectors. Now, let sigma be an isometry, and we try to find the matrix of sigma with respect to this basis v1 and v2. The first column has to be the image of v1. v1 is an isotropic vector, so its image must be an isotropic vector. So it's either in the span of v1 or in the span of v2. Suppose the image is in the span of v1, then it's going to be some multiple here, of v1, and this is 0. Now the image of v2 has to also be an isotropic vector. It cannot lie in the span of v1 because the matrix sigma has to be invertible, so it must lie in the span of v2. Similarly, if instead the image of v1 lie in the span of v2, then the matrix has to be of this form. Because we know that the determinant must be plus or minus 1, we arrive at the following description of the group of isometry of the hyperbolic plane.